There are several things I would like to do as we talk about moment of inertia. First, I would like to introduce the concept of inertia, and in the rotational sense, moment of inertia. We'll derive the equations that are used to calculate it. And then I want to introduce something called the parallel axis theorem, useful when you're calculating moments of inertia. And then last, I want to come back and revisit the topic of rolling without slipping, particularly from the context of moment of inertia and rotational kinetic energy. So we'll take another look at rolling without slipping. Okay, first let's talk about the concept of inertia and moment of inertia. The word inertia means the tendency to continue doing what you're presently doing. In mechanics, we can think of an object's inertia. If we return to translational motion in our thoughts here for a minute, imagine that we have a gigantic boulder. Maybe we're in space, so it's just floating there. That boulder, because it has a lot of mass, has a lot of inertia. Whatever it's doing, it's going to tend to keep doing that. And if we want to change that state, we have to exert a force on it. The more mass it has, the more inertia it has, the more force we have to exert to get the same change in the motion. That's the idea of inertia, the tendency to continue doing what you're presently doing. If you're sitting on the couch watching TV, very often the longer you sit there, the more inertia you have, the more you want to just sit there and do nothing. It's harder and harder to get up and do something. That's inertia. In the rotational sense, we talk about moment of inertia. Objects that are rotating also have an inertia, but in this case it depends not only on how much mass there is, it also depends on how the mass is distributed. Suppose you have a stick, and on it there are some weights that can be slid back and forth. And we want to pivot the stick around this end and make it move back and forth this way. Your intuition could probably tell you that it's easiest to make this stick and the weights that are attached to it rotate in this way if you move these weights this way close to where the pivot is. If the mass is close to where the pivot or the axis is, it's going to be easy to make this stick rotate back and forth. But if, on the other hand, you take these masses and you move them all the way to the end so that you're holding a stick with a bunch of mass at the very end of it, it's very hard to rotate it in the same way. It's very hard to change the rotational motion. Just by changing where these masses are located, we have changed the rotational inertia. So when it comes to rotational motion, the concept of inertia involves more than just how much stuff there is, how much mass there is. It also involves where that mass is located relative to the axis of rotation. And we see here that the more mass you have farther away, the more rotational inertia you have. So that's the idea behind this moment of inertia. Let's see now how we can obtain an equation for how to calculate it. I want to go at this with the idea of kinetic energy. So let's suppose we have a coordinate system here with some object that we're going to rotate around. So here's a flat pancake-like object. There's an x-axis and a y-axis, and we're going to pick a pivot and make this pancake-like object spin in the xy plane. Now suppose the point that I pick is the center of mass that we talked about a while ago. So there's the center of mass right there. And we're going to make this thing rotate around so that every point's going to spin around like this. I would like to write down this rotating object's kinetic energy, capital K. And I'll call it K sub R, the rotational kinetic energy. We know from the last talk that what this ought to equal is half I omega squared, where I is the moment of inertia and omega is the angular speed that this thing is rotating with. But let's see how to get that. Even though this is a pancake-like object, let's think of it as being composed of a whole bunch of discrete objects. So imagine that we broke this pancake up into little tiny rectangles or blobs. And these rectangles or blobs filled this thing so that they're going everywhere here. And I just filled this whole thing with these rectangles. Each rectangle might have some mass. So this one right here might have a mass that I'll call m sub I, the mass of the ith little rectangle. Because this pancake is moving, that little rectangle that I'll shade in here not only has mass, but it's also moving. It has a velocity. So that little rectangle has kinetic energy. And if I want to know the kinetic energy of the whole object, of the whole rotating object, what I can imagine doing is performing a sum, adding up half mv squared for this one, plus half mv squared for that one, plus half mv squared for that one, plus half mv squared for every other little rectangle in this object. The rotational kinetic energy of this thing is the sum over all of the little rectangles of half each little rectangle's mass times each little rectangle's velocity squared. Now let's see if we can rewrite and simplify this. Because this object is rotating, the velocity vectors are all going to be in the tangential direction. So there is the velocity of that little piece. This little piece here is going to have a velocity this way. This one will have a velocity over here. Every single one of these little rectangles is going to trace out a circle, and all of their velocities are equal to the tangential velocity that we talked about before. So all of these v's are the r times omegas, where the r is the distance from the pivot, from that dot to the object. So there's r sub I for that piece. And I need to add up now half m times r squared omega squared for every little object. So I get sum over all the rectangles of half m r I squared omega I squared. I can factor the half out of this summation. So I have half the sum over all the rectangles. I forgot an I up here, of m sub I r sub I squared. But notice that if the object is rigid, if it all rotates together, then omega is the same for every piece of this object. If the whole thing is rotating together, every piece of it has the same angular velocity. Different pieces might have different distances from the pivot, different r values, but they'll all have the same omega. So I can collect all of this stuff together and have one common omega. And now we see the equation that we need. The rotational kinetic energy is half I omega squared, where I, the rotational analog of mass, the moment of inertia, is the sum of each individual mass times the distance squared from the axis of rotation. So when we have a collection of discrete objects, like we're thinking about all of these little rectangles here, the moment of inertia is the sum of each mass times the distance squared from the pivot to the mass. So the more mass you have farther away from the axis, the bigger the moment of inertia, like we talked about before. So that's how you calculate the moment of inertia for a collection of discrete objects. Suppose we had not a collection of discrete objects, but we had a continuous object. Let's think now of this pancake-shaped object as one continuous thing. What we can imagine doing is shrinking these little rectangles so that they become infinitesimally small, When we do that, we have to add up an infinite number of them, and what happens is that summation turns into an integral, and we end up integrating r squared dm. When you have a continuous object, this is how you calculate the moment of inertia. I'll talk more about this and go through some examples in the next talk. But this gives us the two equations we need to calculate moments of inertia. When you have a collection of discrete objects, you use the top one. I'll put discrete objects here, individual objects. When you have a continuous object, use the integral form. All right, so that's how we calculate moment of inertia. We'll do some examples in the next talk. There's a couple of other things that I want to introduce to you here. We want to talk about the parallel axis theorem, and we need to talk about rolling without slipping again. Let's first talk about the parallel axis theorem. The idea behind moment of inertia is that the rotational inertia, the tendency of a rotating thing to keep rotating the way that it's rotating, increases as you get more mass far from the axis of rotation. In this object up here, we said at the beginning that we were supposing this was the center of mass, the mass-weighted average position of this object, and it was rotating around there. Now let's imagine what happens if I take the axis of rotation and move it farther out here. Suppose I move the axis of rotation here, so that now every piece of this object was rotating in circles around this way. We should be able to see that on average, the mass has gotten farther away from the axis of rotation, so the moment of inertia should go up. Without deriving it, it should make some sense to see that the moment of inertia is the smallest when an object rotates around an axis through the center of mass. And if you move that axis from the center of mass, the moment of inertia is going to increase. In fact, the relation that I'm not going to derive is given by this. The moment of inertia, in general, is the moment of inertia about the center of mass plus the total mass of the object times a distance d that you move the axis parallel to itself. Let's look at that up here. The axis started out right here. If we know the moment of inertia around that axis, that gives us this term. Now suppose I want to move the axis, and I want to rotate it around this point instead. I move this axis a distance d, and I'm moving the axis parallel to itself. I'm not rotating the axis. The axis is coming out of the screen towards me here, and it's still coming out of the screen towards me here. I've moved the axis parallel to itself. That's why we call this the parallel axis theorem. And I moved it a distance d. So the moment of inertia goes up by total mass of the object times the square of the distance that I moved it. This bean-shaped object has a mass capital M. So this is the parallel axis theorem. Once you know the moment of inertia of something about an axis through its center of mass, that's the smallest the moment of inertia is ever going to be. If you move the axis some distance d away, without rotating it, you increase the moment of inertia by an amount of the mass times d squared. All right, so let me erase some of this and get ourselves some room to talk about our last thing, which is rolling without slipping again. So let's erase this stuff. And I'm going to shrink these expressions so we can keep them. Let's shrink it and move it up here. And do the same thing for this. We'll shrink it and move it up here. And take another look at rolling without slipping. Here's the motion again that we are talking about. We have some surface that our object is going to roll without slipping along. And let's imagine that the wheel is right here, so that as it rolls along, it looks something like this. It's rotating around with some rate omega, so that the wheel is moving sideways at speed v. What I want to show you here is that this motion, this rolling without slipping, is in every way equivalent to the sum of two other motions. If something rolls without slipping, it's equivalent to the wheel translating without rotating, plus rotating without translating. Let me draw that, and we can see it a bit better. I'm going to give myself a reference line here. So there's the center of the wheel. Let me draw two more wheels. First, a wheel that is translating without rotating. So here's a wheel that is just scooting sideways. It's not spinning at all. So that every point on this wheel is moving with a velocity v. I'm going to draw several velocity vectors here. They all have the same length v, which is the same as this length right there. So there's a wheel that is translating without rotating. Now let me draw another one so that we can add the motions together. So translating without rotating, plus here comes a wheel that is rotating without translating. So this is a wheel in purely rotational motion. It's rotating this way, but it's not translating at all. So the velocity on the rim of the wheel would look like this. Velocity v here. Here it's going to be moving down, here this way, like that. And the claim that we're not going to prove, but hopefully it makes sense so that we're comfortable using it, is that translation without rotation plus rotation without translation equals rolling without slipping. Let's look at how the velocity vectors add. First, if we look at this velocity at the center, that point has a velocity v from the translation, nothing from the rotation, and it has velocity v in the sum, which is good. A point at the very bottom has this velocity v due to translation. From the rotation without translating, the velocity is going the other way, so when we add those two vectors together, they will cancel. And this point right here is momentarily at rest. As the wheel rolls down the road without slipping, the point of contact with the surface is momentarily at rest. And if we think about that for a minute, we can see that must be the case. If it wasn't the case, as wheels rolled without slipping, they would always be sliding across the surface, and in the case of a car, we would always be peeling our tires out and smoke would always be rising up. The point of contact between the wheel and the road is momentarily at rest. Now let's look at a point at the top of the wheel and see what its velocity is. At the top of the wheel, we have this velocity v plus this one, and we end up with a point at the top of the wheel moving twice as fast as a point at the center. There's a line that goes out here like this. And in fact, that's the case. The top of a wheel is moving twice as fast as the center of the wheel, because this is the axis of rotation. That's the stationary point. So the farther away it is, the faster that point's moving. So the thing to remember here is that rolling without slipping, I'll call this R without slipping, RWOS, is equal to the sum of two other motions. Translation without rotation plus rotation without translation equals rolling without slipping. And that means if I want to write the kinetic energy of this thing, the kinetic energy of something that is rolling without slipping, I can write it this way. So the kinetic energy of something rolling without slipping is the kinetic energy of the thing translating without rotating plus the kinetic energy of it rotating without translating. So you can always express the kinetic energy of something rolling without slipping as the sum of two kinetic energies, purely translational motion plus purely rotational motion. This will come up in a lot of the examples and problems that we work, and this is where it comes from. It comes from the fact that you can always treat rolling without slipping as the sum of a pure translation plus a pure rotation. Let's turn our attention now to some moment of inertia calculations and some example problems.